Welcome back to lecture number 15. In the previous lecture I discussed left and right induced global stable homotopy types. So these are orthogonal spectra that are in the essential image of the left adjoint or the right adjoint to the forgetful functor from global to non-equivariant stable homotopy. These two adjoints are fully faithful, so they implement a copy of the non-equivariant stable homotopy category inside of the global stable homotopy category, in one case on the very left and in one case on the very right. I've proved some criteria for detecting when an orthogonal spectrum is left or right induced, and here the criteria are again: an orthogonal spectrum is left induced if and only if it has constant geometric fixed points, and the precise statement is that for every compact Lie group G, a certain natural map from the non-equivariant stable homotopy groups of X to the G geometric fixed point homotopy groups is always an isomorphism. The map comes from combining the inflation map along the only group homomorphism from the group G to the trivial group, and then the geometric fixed point map. There's also a criterion for when an orthogonal spectrum is right induced, and these are the global Borel cohomology theories. The criterion is here on the whiteboard again. For every compact Lie group G and for every G space A, the G equivariant X cohomology of A is supposed to be isomorphic to the G equivariant X cohomology of EG cross A via the projection. So an orthogonal spectrum is right induced if it looks as if every G space were free. It doesn't see the difference when you free it up by taking product with EG. If this happens, so if X is right induced, then moreover the G equivariant X cohomology of A is naturally isomorphic to the non-equivariant cohomology of the Borel construction, and this is why we think of the right-induced global homotopy types as global Borel theories. Today I want to establish the standard T structure on the global stable homotopy category, and thereby in particular construct Eilenberg-MacLane spectra for global functors. The concept of T structures was introduced by Bernstein, Beilinson and Deligne in an asterisk volume that was called Perverse Sheaves, or in French, Faisceaux pervers. So they wanted to construct abelian categories by a technique of taking complexes of sheaves on some suitably stratified space, and then you test whether these complexes have the cohomology or the homology only in certain degrees, but you test this at different levels, at different heights, depending on the strata. So they introduced a general formalism that handles their particular situation, but that has also been interesting and important in lots of other situations. So they introduced this concept of a T structure on a triangulated category. So here's the definition. A T structure on a triangulated category T is a pair of two full subcategories. Is a pair T greater equal 0, T less than equal to 0 of full subcategories. That satisfy three conditions. And then in specifying these conditions, and also later, it's convenient to introduce a piece of notation. So T greater equal to 0 is given, and then we set T greater or equal to n. We define this as T greater or equal to 0 shifted by n, so this is the shift in the triangulated structure, and similarly for the less than or equal, T less than or equal to n is defined as T less than or equal to 0 shifted n, and n can be any integer, positive or negative. And now here are the three conditions. So the first one is, for all x in T greater equal to 0, for all x in T greater equal to 0, and all y in T less than equal to -1, there are no morphisms from x to y. So one important motivating example for us will be the non-equivariant stable homotopy category. I'll discuss this in more detail later. In this example, this will be the connective spectra, so those where all the homotopy groups in negative dimensions vanish. This will be the spectra where all the homotopy groups in 0 and positive dimensions vanish. And then it's a standard fact that there are no morphisms from such connective spectra to co-connective spectra, and then a shifted one further down. So the second condition just says that if you have t greater or equal to 0, this is contained in t greater or equal to -1. I mean, this is kind of a suggestive thing. Of course, if you're greater or equal to 0, you should in particular be greater or equal to -1. And also for the other one, so t less than equal to 0 is containing t less than equal to -1. So here the containment is in the other direction. And then the third one says that everything can be split up, every object decomposes via a distinguished triangle into something that is non-negative and something that is strictly negative. So for every x in T, there is a distinguished triangle of the following form: A mapping to X, mapping to B, and then A shifted by 1 with certain morphisms that we don't care about. And the important conditions are such that the A is non-negative, so A is contained in T greater or equal to 0, and B has the negative stuff, so B is in T greater or equal to -1. So this is assuming that we have a sort of Postnikov decomposition, like in the non-agrarian stable homotopy category. This would be an arbitrary spectrum with homotopy groups possibly everywhere. This would be like a connective cover, which has the homotopy groups in degree 0s and above, and this will have all the homotopy groups in negative degrees. So this is not exactly how Bernstein, Beilinson, and Deligne formulated their axioms originally, because they were coming from algebraic geometry, and there the tradition is usually to consider co-chain complexes with the differential going up. In topology, we would usually consider chain complexes with a homology going down, or spectra, which kind of the topological analogs of chain complexes with differential going down, and that means that we have reversed the grading conventions with negative and positive. So traditionally, these decorations would be on top, and then you would have to think of a cohomological grading, and we're thinking of a homological grading. So one more definition: the T structure is non-degenerate if, first of all, the intersection of all the non-negative things is 0. So intersection of all n greater equal to 0 of t greater equal to 0 only contains 0 objects, and similarly for the other ones, and the intersection of all n greater equal to 0 t less than equal to 0 only contains the 0 objects. And in the non-agrarian stable homotopy category, this is just the statement: if all the homotopy groups vanish, then you're the 0 object. Here are some consequences of the T structure axioms. I don't want to prove these facts, but I'll give you the appropriate references to the Bernstein, Beilinson, and Deligne paper. So the first property is that the inclusion of one of the two categories of T greater equal n into T has a right adjoint, and the right adjoint is denoted tau greater equal to n. It goes from T into T greater equal to n. So this is called a truncation functor. You can think of it as truncating at level n and above and throwing away the stuff below n, so the homotopy groups or homology groups in n-1 and below. And then there's the dual statement. The other inclusion, t less than equal to n into T, has a left adjoint. It's then written T less than equal n, going from T into T less than equal to n. So to give you something to think about, if you look at the second case, for example, there's a left adjoint, so every object x will come with a morphism to t less than equal to n of x, because that's the left adjoint and then the inclusion. And this is the unit of the second adjunction. And in the examples we care about, spectra, equivariant spectra, global spectra, this will be a thing which has the same homotopy groups as x in dimensions n and below, possibly equivariant, or more precisely, this morphism will be an isomorphism on homotopy groups in level n and below, and this will have vanishing homotopy groups or equivariant homotopy groups in level n plus 1, dimension n plus 1, and above. So then if you choose these adjoints, so given choices of adjoints as above, there's a preferred natural isomorphism for every m less than equal to n. There is a preferred natural isomorphism from t greater or equal to m after t less than or equal to n, or rather composed with the inclusion, to the same the other way around, less than equal to n, so t after equal to n. So this is saying that if you want to have an object like a spectrum, you want to pick out the stuff in some interval between m and n including, then you can first throw away the stuff above and then the stuff below, or you can do it in the other order and you'll get the same result. The final property I want to mention is the heart. So the heart of the T structure, which by definition is the intersection of t greater equal to 0 and t less than equal to 0, and I will use a math Carl H notation for this to designate heart. So this is an abelian category. In contrast to a triangulated category, which is extra structure on a category, abelian is just a property of a category. And here we're looking at this category H, which is relatively easy to see that this is an additive category. But the fact that it's an abelian category is a very strong property. So at this level of generality, that's pretty much all you know about it, is some abelian category. In this generality, you will not know whether this has enough projective objects, whether it has enough injective objects, if it has sums, infinite products, whether it's Grothendieck abelian. This is all you get in this generality, and we will be interested a little bit later in criteria for when you can actually identify more concretely what this abelian category, the heart, is. So moreover, the functor t less than equal to 0 after t greater or equal to 0, or because of this you could do it in the other order. So this will be a functor from the triangulated category into the heart, is a homological functor. So this is a slight extension of the notion of a homological functor that I've talked about in the previous category. There we had functors from triangulated categories to abelian groups, and they were homological if they take distinguished triangles to exact sequences of abelian groups. Now this is an abelian category, so we have a notion of exactness, and homological just means it takes distinguished triangles to exact sequences, 4-term exact sequences in this abelian category, and then of course you can rotate in both directions. So what this is kind of saying is that the whole situation is as if you were in chain complexes and we had the H0, the zeroth homology functor to the module category, or as if you were in spectra and you had the pi0 functor to abelian groups. This truncation is something to the heart which behaves like taking zeroth homotopy groups or taking zeroth homology groups. So let me briefly write two important examples on the board that I've already mentioned in words. I will get back to those examples in more detail later, but so that you have something to think about. So the first example is D of R for a ring R. So this was the unbounded derived category of a ring. So it's the localization of the category of Z-graded chain complexes under quasi-isomorphisms. In this situation, you use homology to define what you mean by non-negative and non-positive. So the greater equal to 0 part will be all complexes X in the derived category with the property that the homology vanishes in negative dimensions. The non-positive part will be sort of the opposite. These are all x in the unbounded derived category such that the homology vanishes in positive dimensions. And then, of course, there's things to check in order to verify these axioms. And another example that I've mentioned in words already a bunch of times is we take the non-equivariant stable homotopy category. And then we'll take homotopy groups and make the analogous definitions. So stable homotopy category greater or equal to 0 are all spectra X, such that the homotopy groups vanish in negative dimensions. So these are the connective spectra. And in the other direction, as H less than or equal to 0 is the opposite, these are all X, such that the homotopy groups vanish in all positive dimensions. So these are the co-connective spectra. I will return to these examples later, but you might want to check that in this particular situation, the heart would be the category of R modules, the Abelian category of R modules here, and this truncation functor corresponds to taking 0 of homology. And here the heart is the category of Abelian groups, and this truncation functor corresponds to the 0 of homotopy group functor. I will devote today's lecture to explaining how you can generate T-structures in a very systematic way from a set of compact objects. This will come in two flavors. One way of generating is very general. It's so general that it's not particularly useful for our purposes. And then in the second step, we'll add another condition, a positivity condition, to make it more useful. Let me start with a very general way of generating a T-structure. So we'll let T be a triangulated category. With sums. So particular infinite sums. We let script C be a set of compact objects. Eventually we'll take this to be a set of weak generators, but right now this is not necessary. Let C pointy brackets plus denote the smallest subcategory. Of T that is closed under sums. Including infinite sums and closed under cones. What does this mean? i.e., for every distinguished triangle, A to B to C to A shifted by 1, where the first two objects are in the class, with A, B, in C, pointy brackets plus, then also the third object. Also C belongs to the class. This is what I mean by closed under cones. So if you have a class that is closed under cones, and it has at least one object, that it contains a 0 object and all 0 objects, because you can take one object and the object again and the identity, this will be a 0 object. So such a class, unless it's empty, contains all 0 objects. It's also automatically closed under suspensions, because you could take an object here, the 0 object here, and then here you'll have the suspension. Of course, in the definition, we're breaking the symmetry. We're closing under cones to the right. So such a class will typically not be closed under coning to the left, or desuspending, or taking fibers. And in particular, it will typically not be closed under desuspensions. So now here's a very general theorem how such things generate a T-structure. Let T be a triangulated category with sums. objects. Then we make a definition. We define the orthogonal complement of this. So we define C perp as the class of all y and t that have no morphisms from this class. So such that for all x in C plus there are no morphisms. T, x, y is 0. And then the statement is that you get a that you get a T structure, and the pair the stuff that's generated by C under sums and cones, together with this complement, and then shifted up by 1, is a T structure on T. As I already said, this result is so general so that its use is also a little bit limited. In this generality, it's very hard to get any information about what the heart of this T structure, this abelian category, looks like. So if you want some concrete identification of the heart with some module category or category of additive functors, and that's really what we are after, you will need additional conditions on the objects C in this class a little bit later. But this also illustrates that T structures really exist in abundance. There's an extremely general method for producing them. Now I will explain that if we add a kind of a positivity condition and also assume that this class of compact object generates, then we get a much better, much more manageable T structure. We consider a triangulated category with arbitrary sums in a set C of compact weak generators. In particular, the triangulated category is then compactly generated. We impose the following positivity condition on the generators. There are no non-zero morphisms from any negative shift of a generator to any other generator. In our main examples, this will correspond to the fact that the homotopy groups of suspension spectra vanish in negative dimensions, even equivariantly. If the positivity condition is satisfied, there might still be other sets of compact weak generators that do not satisfy positivity. We prove 5 different statements. The first fact is that the class generated by C under sums and cones is precisely the class of C connective objects, i.e. the ones that have no non-zero morphisms from negative shifts of the generators. The second fact is that the class generated by C under sums and cones, which by the previous claim is the class of C connective objects, together with the class of C co-connective object, forms a non-degenerate T structure. The third part identifies the heart of the T structure with the C Eilenberg-MacLane objects, i.e. the ones that have no non-zero morphisms from strictly positive or strictly negative shifts of the generators. Part 3 is a direct consequence of parts 1 and 2 and is mainly stated for easier reference. The fourth claim says that the heart, considered as a full subcategory, has infinite sums, and that these are given by sums in the ambient triangulated category. The fifth part says that the zero truncations of the original generators are projective objects in the abelian heart, and that moreover they are compact generators of the heart. As I'll explain in the next lecture, abelian categories with a set of compact projective generators are very special, namely they are generalized module categories. I do not know of a reference for the theorem in exactly this form, and I don't know if any particular person should get credit for this. Several variations and special cases have been published, and in any case, the theorem is certainly not due to myself. I'm about to prove a theorem with multiple parts, so it could be easy to lose track of exactly where we are. So I will overlay the hypothesis of the entire theorem and always the statement that we're just in the process of proving in the top part of the video. Part 1 claims an equality between two classes of objects, and I will show this by showing the two inclusions separately. So we consider the class math card S, the class of those objects, x in T that satisfy the characterization, so such that there are no maps from C shifted by in N into X, so such that this is 0 for all C in the class of generators that we've chosen and all N less than 0. So by the positivity hypothesis, that exactly means that the class C itself is contained in this class X. Now we're going to use the assumption that the objects in C are compact for the first time. So since all objects in C are compact, the class X is closed under direct sums. Arbitrary sums. Because after all, we're mapping something compact into a direct sum, and that we can take out. Moreover, I claim that the class X is also closed under cones. The class X is closed under cones. At X to Y to Z to X shifted by 1 be a distinguished triangle. Assume that the first two are in the class. Suppose that X and Y belong to this class of objects. Now we're going to test this condition for the other one, for Z, so we get an exact sequence. So we're mapping such an object in, we get T, C, N mapping into Y, T, C, N mapping into Z, and then we'll get T shifted by C shifted by N into X of 1, but those we can cancel. So C N minus 1 into X. Now this group is 0 by the hypothesis that Y belongs to the class. This is 0 by the hypothesis that X belongs to the class, and luckily because the number went down by 1 and not up by 1, so we conclude that this is 0. And this is for all n less than 0, and then this number of course is even more negative, so this proves that the cone Z also is in the class. So we have a class that is closed under cones, under sums, and contains the generators, and so we conclude that it in particular contains the smallest class with these closure properties, so C plus is contained into X. The reverse direction I will prove a little bit later, because I first want to prove the second claim in this statement. Let me now prove part 2 of the theorem, which says that we really have a non-degenerate T structure. The T structure itself is 3 separate properties, so I'll prove them one after the other. So let's start with the first one. So for this, we let math Cal A be the class of those objects, of those A and T, again, which is kind of a complement. It's characterized by a vanishing condition, and is such that it has no maps into any objects for all, such that this is 0 for all X in what was generated by T less than equal to 0. And we observe a bunch of closure properties. Then first of all, the original class shifted up by 1 belongs to this class A. This is just a restatement of the positivity hypothesis that we had. The next observation is that because the functor T blank X takes sums to products, the class A is closed under sums. So it contains the generators, it's closed under sums. We also have to show that it's closed under cones. So for this we consider a distinguished triangle. Let A to B to C to A shifted by 1 be a distinguished triangle. such that A and B are in the class. A, B are in the class abstract A, and we have to show that then also this object is in the class. And of course of this we just hom it into a test object X, taken arbitrarily from this one. So then we'll get an exact sequence. So now we're homming into X, so the variance turns around. So we have T from A shifted by 1 into X, going from T, C into X, T, B into X. And then for all X in class of C greater or equal to 0, we have that this is 0 by hypothesis. This is also 0 because we're shifting just in the right direction. We're shifting up here, equivalently we're shifting down there. So that's in here, so we can conclude that this is 0 for all test objects X. So C is also in this class, and the class is closed under cones. So because it contains the generators shifted by 1 and is enclosed under sums and cones, we can conclude that C plus shifted by 1 is contained in the class A. And if you expand what this means, this is exactly the first property in the list of 3 properties of having a T structure. So the second thing to check for having a T structure is even easier. So that's just the property that C plus shifted by 1 is contained in C plus. Now, because by closing up under cones in the right direction, I explained this earlier, we're also closing up under suspension, so in particular we have this inclusion. And then when we pass to the complements, when we test out of this, the inclusion reverses and the shift moves to the other direction. So this formally implies by just testing against these classes that C less than equal to 0 shifted up by 1 contains C less than equal to 0, and that was the second property. The third defining property of a T structure requires us to construct a distinguished triangle with specific properties. Here's what we have to construct in our situation. So we need for an arbitrary object X in the triangulated structure a distinguished triangle of the form A mapping to X, mapping to B, and then A shifted by 1. And we need that A should be in the class generated by C under cones and sums, and B should be in the class pointed bracket C less than equal to -1, the downshift of less than equal to 0. Before I go into the construction, let me pause for some historical comments. As the length of the argument will show, this is kind of a key step in the entire theorem. This is an instance of what more generally is known under the process of Bousfield localization. This idea goes back originally to an idea of Frank Adams, who presented it in a talk at the University of Chicago in 1973. Obviously, I was not at that talk because I had to attend kindergarten, but fortunately the talk survived because Zig Fyodorovich took notes that eventually he tagged and put on the archive some 10 years ago. Adams's construction of what we now call Bousfield localization had a flaw because he was taking a sum over a proper class of things, and that brings you into all sorts of set theoretical and logical problems. A little bit later, Bousfield fixed the argument by imposing a cardinality bound. So originally this was really for Bousfield localization at a generalized homology theory, and then you have some spectrum around. The spectrum has homotopy groups, and these have a cardinality, and Bousfield used that to bound the objects that you have to take sums over and then get down to a proper set as opposed to a class of objects. Bousfield's arguments were soon taken up by other people and generalized and extended to different contexts, so for example to triangulated categories, and they are now part of the general toolkit of people working in homotopy theory, algebra, and triangulated categories. This kind of distinguished triangle appears explicitly in Bousfield's second paper on the subject, localization of spectra with respect to homology, in this special case where we at the stable homotopy category as a triangulated category. We are operating under the hypothesis that the objects we want to localize with respect to are compact, and that simplifies the general argument quite a bit, because a certain process of coning of maps, coning of objects, only has to be iterated countably number of times. In general, you would have to do some kind of transfinite, more infinite construction. All right, let's now construct this distinguished triangle. So we're given X, and we have to construct A, B, and the morphisms here. So we construct the A by induction and then by a kind of colimit argument. We inductively construct objects AN in the class of C plus, and morphisms IN from AN to AN plus 1, and morphisms UN from AN to X, such that UN is UN plus 1 composed with IN. It's probably easier to remember this diagrammatically, so we're going to have A0 mapping to X via U0, then I0 to A1 mapping to X via U1, A2 via I1, U2, and so on, all the way to infinity, and then we're going to take some colimit process. The induction starts as follows. So we set A0 to be a big sum indexed over a set of things, and the set runs over the following data. First of all, over all objects C in this set of compact objects C. Here we've insisted that it's a set. Then we're running over all k greater or equal to 0, so not over all integers, only over the non-negative ones. And then we run over all elements X in morphisms in T from C to the k of X. So for every map from a positive shift of one of the generators into X, we take something, and we take exactly a copy of what we're mapping out of here. We take a copy of C to the k. Since all the objects little c are in the class cal C, their positive shifts are, and hence the direct sum is, so this entire object is in the class C plus. It also comes with kind of a tautological map back to X, the map U0, and this is, let me say, it's X on X. It's a tautological map because summands are indexed by maps, and on the summand that is indexed by little x, you take exactly the map, little x. So that was the first step in the construction, and now we're iterating it by coning off copies of shifts of objects in C. So for the inductive step, we're now assuming that AN has constructed. Suppose AN and UN from AN to X has been constructed. Now we're going to construct the next one. We'll first define an auxiliary object. We set Dn to be, again, a similar construction as here. We take a big sum. First of all, indexed over all objects C in this set of compact objects that we started with. Again, for all k greater or equal to 0. But then we're not indexing by all possible morphisms, but only by those in the kernel of the map you get by applying maps out of Ck to the element Un. So we're now looking at all morphisms from Ck into the previous object An, but only those that become 0 when you compose with Un, that become 0 when you go to X. So this again comes with a tautological map to An, because after all, we're indexing now by things which are maps from Ck to An. So this comes with a tautological map, Dn to An. So let me just write tautological. Now we choose a distinguished triangle. This is one of the axioms of a triangulated category. Given any morphism. It's part of a distinguished triangle. So this defines the next object, an plus 1. This defines the morphism an, and then as part of the distinguished triangle, we also have the shift dn. This defines the next object and the morphism in. So how we're going to get the morphism to x, whether this is also essentially clear by construction. The composite of this map is 0 because we're exactly indexing over x's that live in the kernel of un. So by design, on every summand of dn, this composite is designed to be 0, and then the axioms of a triangulated category guarantee that when it can extend over this, we choose un plus 1 here. So the an plus 1 and the un plus 1 are choices. They're by no means unique or functorial or anything like this. But nevertheless, this is how we inductively construct the data. And now we need to pass to some kind of sequential colimit. We've just constructed this sequence of objects and morphisms in our triangulated category with compatible maps down to the x that we started with. We started with a big sum of positive shifts of copies in the class C, and then we always comment off sums of positive shifts of copies, so we always stay in this class pointy bracket C plus. All the ANs are in this class. So now we're going to take a homotopy colimit of this sequence, and this needs a little bit of explanation. After all, triangulated categories tend to not have very many colimits, and homotopy colimit is not a colimit in the homotopy category. So I have to explain what this means. In general, this can be a fishy subject, but for the homotopy colimit of a sequence, there's an ad hoc construction that works very well, in particular in this situation. So let me explain what this is. So let A be a homotopy colimit of the sequence. Of the sequence, i.e. defined by a choice of distinguished triangle. So we're taking a direct sum of all the ANs for n greater or equal to 0. We take another direct sum of all the ANs n greater or equal to 0. And here we take a map that's sometimes denoted by 1 minus shift. So if you think of a morphism from here to here as a big infinite matrix, so this is the matrix which has the identity of an on all the diagonals. And then here it has minus I0, here it has minus I1, here it's minus I2, and so on. So each summand goes to exactly 2 summands on the other side. It goes to the identity by itself, and it goes to minus the map in to the next summand. It goes to 0 in all the other summands. And then, like every morphism in a distinguished triangle, also this one can be completed to a distinguished triangle, and this is what defines A. So the triangle then discontinues with direct sum of the ANs shifted by 1. So this again is a choice, and it is not in general functorial. Nevertheless, this ad hoc construction, that's called the homotopy colimit, has a weak colimit property, and that's all we're going to need. You might want to check if you did this not in a triangulated category, but in the category of abelian groups, and you took the actual colimit or co-kernel of this analogous map, then you would get a colimit of the sequence. That's kind of the motivation. So here's a little lemma. For every compact object C in T, the canonical map from the colimit n greater or equal to 0 of maps from C into the AN. So these are abelian groups, and that's just the colimit of abelian groups. In this, it's a canonical map to T from C into the homonym, in this case the A. This is induced by the various components. So the components of this morphism give you lots of compatible morphisms from A into A. They are compatible because this composite is 0, so we have this canonical map, and this is an isomorphism. This definitely needs the compactness. It's not going to be true without that in general. And the proof is easy. This is a distinguished triangle, so we take maps out of C into this distinguished triangle, and we get an exact sequence. The the following sequence is exact. So we're mapping C into the direct sum of the ANs, T, C into the direct sum of the ANs, T, C into A, and then something else comes. So this is applying C to the 1 minus shift map. Now we're going to use the compactness. The compactness means that the canonical map from the direct sum outside, T of C into the ANs, is an isomorphism of abelian groups. We're using the same again here. The direct sum of maps from C into the AN is an isomorphism here. And under this becomes the 1 minus shift map, but now in the context of abelian groups. And if you did the exercise that I mentioned a little bit earlier, you'll see that here we actually get the colimit of T, C into AN. So in the category of abelian groups, this map is always injective. That's the first thing to check. And moreover, the co-kernel is naturally isomorphic to the colimit. Here, this is the induced map. So now, because this is injective, it means that in the what would usually be a long exact sequence, one of the maps, or every third of the maps, is injective. So the long exact sequence actually splits up into lots of short exact sequences. It means it doesn't matter what comes next because it splits up into short exact sequences. This is surjective. Now we have two short exact sequences, an isomorphism here and isomorphism here, so we're also going to have an isomorphism here. So this is the justification that the homotopy colimit, from the perspective of mapping compact things into it, behaves a lot like the colimit would. We constructed the object A as the homotopy colimit of the sequence, which meant choosing a distinguished triangle like here. All the objects AN were in the class pointy bracket C+, and since their direct sums are in there, because this class is closed under sums, and because the class is closed under cones, the A will again be in the class C pointy brackets plus. That's what we wanted. Now we also need a morphism to X, and this we get as follows. We have a morphism down to X consisting of the family of the morphisms UN. UN on the nth summand altogether is a morphism from here. And this compatibility of all these little triangles, of course, says that U1 minus the composite of U2 and I1 is 0, so that exactly means that this composite is the 0 map. And then because we have a distinguished triangle, it means we can choose an extension here, again not unique, that we call U, and that gives us a morphism from A to X. And if we compose this with the summand inclusion AN, then in here we exactly get UN. So this is kind of, you can put the A here and you get a compatible morphism down here. Now we can construct the distinguished triangle that we need. So we choose yet another distinguished triangle. Now we start with this morphism just constructed, U from A to X. We choose some B as a cone, and it goes to A plus 1. And the claim is that this does the job. So we've already seen that this is in the pointy bracket C plus in the class generated by C under cones and sums. So all we need to show, so we must show that the B is contained in the pointy brackets C less than equal to minus 1. And then we're done, i.e. if you expand what this means we have to show that morphisms from positive shifts of objects in C into B are 0. So we must show that this vanishes for all C and C and for all K greater than equal to 0. We will show this by using the long exact sequence we get from here by mapping C to the shift K in. So we want to check what this morphism U does when we take maps from C shifted by K into it. The first observation is that we get a surjective map, and this we see as follows. So we have A0. So this was, if you remember, a big sum over all C in C, all K greater or equal to 0, and then of all X in maps from CKX to our X, and then a copy of CK, and the map to X was the tautological one. It was little x on the summand index by little x, and we have now factored this through A, and here the map U, and this was our map U0. We apply morphisms from CK into U0. So this is a map from T morphisms from CK into A0 to morphisms from C shifted by K into X. This is surjective by design. Why is it surjective? You know, K is greater or equal to 0, C is in the set of generators, so every element in here is one of these things that we're indexing over. So every element in here has a corresponding summand, and in that summand it certainly has this map which hits the given map on it. So this map has the identity in this summand. So this map is tautologically surjective, and because it factors like this, we can also conclude that maps from CK for any C in C and non-negative K into U is surjective. On the next whiteboard, I'll show that this map is also injective. I just showed that the map TCK into U is surjective for C, one of the chosen compact objects, K greater or equal to 0, and now I'm going to show that it's also injective. So I'm going to do this by a diagonal chase. So let alpha in TCKA be in the kernel of the map TCKU. So what does this mean concretely? We have CK, we have the object A, we have the morphism alpha, and then when we go on via U to X, this composite is 0. So now CK is a compact object, and I'm mapping it into the homotopy colimit, and I just told you that mapping into a compact object into a homotopy colimit gives the colimit of the map. So this concretely means that the morphism alpha will factor through some finite stage alpha n via some morphism alpha prime, and then the canonical map to the colimit that this came with. Now we have this morphism alpha prime. If we go here, and down here, we get the 0 morphism, but this was un. So alpha prime is a morphism such that when we compose with un, it becomes 0. But these are exactly the morphisms that we were coning off in the process of going from an to an plus 1. These were exactly the things that index the summands in what used to be called dn. So this means that when I go on to an plus 1 via an plus 1 is defined so that alpha prime, because it goes to 0 here, becomes 0 there. So this composite is 0. But on the other hand, the map from an to a prime factors over here, over an plus 1 to a. After all, this is the homotopy colimit of all of this. And now we see that alpha is factored as this composite, and the first two morphisms in here compose as 0, so we conclude that alpha is 0 after something, so we conclude that alpha is 0. And this proves the injectivity of this map TCK, U. Now we can complete the argument that B is really in the class pointy bracket C less than or equal to 1. Here's the distinguished triangle that was defining B. It was a choice of cone given the morphism U. Now let's map CK into it and investigate the long exact sequence that we get. So we have a long exact sequence. So T from CK into A, T from CK into X, T from CK into B, T from CK now shifted down by 1 into A, and T, C, K minus 1 into X. So for K greater or equal to 1, this directly shows that this group in the middle is 0. T, C, K, B equals 0 for K greater or equal to 1, because then this number is greater or equal to 0, this number is greater or equal to 0, that map is injective, that map is surjective, so the thing in the middle is 0. For k equal to 0, we have to also use that the group that stands here actually vanishes. For k equal to 0, we would get t of c shifted -1 into A. Now A is in the class generated by C under cones and sums, and we already showed in 1/2 of the first part of the proof. In the part 1 we already established half of, and the half that we showed exactly shows that everything in pointing brackets C plus doesn't receive any maps from negative shifts of the things in the class we started with. So the half of part 1 that we already established shows that this particular group vanishes, and that means also for k equals 0 we get that this group in the middle vanishes. So, because here we still have a surjection. So we also get that t of cb equals 0. And altogether, this shows that b belongs to the class pointing brackets c less than equal to -1, because it doesn't receive any morphisms from C and its positive shifts, and that was the last thing we had to show in here to verify the third part of the T structure axioms. This is almost part 2 of the theorem, just that we also have to show that the T structure that we just established is non-degenerate. The non-degeneracy condition of the T structure again has 2 parts. So for the first part, we consider an object x that is in the intersection over all m in z of pointing brackets c plus shifted by m, and I have to show that such an x is the 0 object. To see this, we consider an object in the set of generators. Let c be in C and some n in Z, and then we analyze morphisms from C shifted by n into x. So because shifting is invertible, we can re-index both sides. So we can write this as t and then morphisms from C shifted to index -1. And then here we have to take x in -1 minus n. But because x lies in all of the shifts of the C pluses, no matter how often you shift in either direction, this still lies in C plus. And we showed in the first part, in the half of the first part that we already established, that everything which lies in pointing bracket C plus doesn't receive any morphisms from negative shifts of the generators. So this is 0. So now we have an object x that doesn't receive any morphisms from any shifts of the generators. And now we're actually going to use the generating property for the first time. It wasn't used so far, so this implies that x is 0 because C is a set of weak generators. For the other half of the non-degeneracy condition, we consider an object y that lies in the intersection all m into z, and then C less than equal to -1 shifted by m, and this is the same as the intersection of all m in z, and then C shifted less than equal to m. And we do a similar argument. We look at some object in the set of generators and some integer z. So we look at morphisms from C shifted by n into y. We do the similar rewriting trick because shifting is an autoequivalence. So this is isomorphic to morphisms from C shifted by 1 and then y shifted by 1 minus n. But this, in particular, also lies in C less than equal to -1, or less than equal to 0, sorry. And so here we have a positive shift, and here we have something that lies in less than equal to 0. So this is 0, and by the same argument as in the first part, there are no morphisms for any shifts, positive or negative, from the generators into y, so this concludes that y is 0 again, because we have a set of weak generators. This completes the proof of part 2. The next thing I want to do is to prove the second half of part 1. So I'm returning to the first claim and prove the second part that we didn't prove yet. So we consider an object x in t, and it has the property that it receives no morphisms from negative shifts of the generators. So T Cn into X is 0 for all n less than 0 and all C in the set of generators. We would like to show that then X belongs to the class pointy brackets C plus generated by C under sums and cones. Fortunately, in part 2 that we already proved, we already constructed a distinguished triangle. So let A, U, X, B, A shifted by 1 be the distinguished triangle of part 2, which we already constructed. And then we know that A belongs to the class pointy bracket C. So what we would like to show is that U is actually an isomorphism, so X also belongs to this class C. If n is positive, greater or equal to 0, then T of C shifted by n into B is 0 because B belongs to the class pointy bracket C less than or equal to -1. So this is something we showed in part 2, and hence it doesn't receive any non-zero maps from non-negative shifts of the generators into this. So how about the other case? So for n less than 0, we have an exact sequence. So we hom morphisms out of Cn into this distinguished triangle, and we only look at a small part of it. Morphisms from Cn into X, then morphisms from Cn into B, and then morphisms from Cn into A shifted by 1, which is isomorphic to morphisms from Cn minus 1 into A. So now n is negative, and our hypothesis on the object X was exactly that we have no morphisms from negative shifts of the generators into X. So this is 0 by the hypothesis on X. And also if n is negative, then n minus 1 is even more negative, and A lies in the class pointy brackets C, and we already showed in the part 1 that we did prove that there are no morphisms from negative shifts. So this is also 0 by the part 1 that we already showed. So we conclude that also the abelian group in the middle is 0. Now we have shown that B doesn't receive any morphisms from any shifts of the generators, positive or negative. So again, because this is a set of weak generators, we can conclude that B equal to 0. And if in a distinguished triangle the cone is 0, then the map before had to have been an isomorphism. So this implies that U is an isomorphism. And that means X is isomorphic to A and hence in the class pointy brackets C plus. And this completes the proof of part 1 of the main theorem. The third claim in the theorem was mostly recorded for easier reference. It's actually a direct consequence of the definitions and of what we have already shown. Indeed, one of the two classes in our T structure consists by definition of the objects that don't have any non-trivial morphisms from positive shifts of the generators. And the other class is exactly the objects that don't have morphisms from negative shifts of the generators. Well, this was not by definition, but this was by part 1. So if we intersect these two classes, we exactly get the morphisms that at most admit morphisms from the generators themselves in degree 0, but no morphisms from positive or negative shifts. So part 3 is a direct consequence of what we've already done. Now, part 4 says that in the situation that we are in, the hard, this abelian category, actually has infinite sums, and more precisely, they are inherited from the ambient category. So we consider a family of objects, X, Xi, be a family of objects in the hard, so which is C plus intersected C less than equal to 0, and we already know that these are exactly the objects Y such that T of Cn Y equals 0 for all C and C and all n not equal to 0. And now I want to show that a sum in the triangulated category is also a sum in the heart. So to this end, we just show that this lies in the heart again. So we look at morphisms from C to the n into a direct sum I in I xi. We're using again that we have compact objects, so you can pull the direct sum out. So this is isomorphic to the direct sum I in I, morphisms from C n into xi. And now if we assume that n is different from 0, all of this will be 0 for n different from 0, because we assume that each of the xi's lies in the heart, and hence also the direct sum lies in the heart. So this means the direct sum I in I xi again lies in the heart. And since the heart is a full subcategory, anything which is a coproduct has the coproduct property in the bigger category and actually lies in the smaller category is automatically a coproduct in the smaller category. The fifth property says that if you take the compact generators and truncate them down so that they land in the heart, then there are a set of small or compact projective generators of the heart of this abelian category. So while the generators by design are in the non-negative part, in the t greater or equal to 0, they will typically not lie in the t less than or equal to 0, so you have to truncate them to get them into there, and this will change the object. So there's actually something to prove here. So we start the different parts of the claim one in order. So the first observation is that if we take t less than or equal to 0 of one of the objects C and C, then of course this lies in t less than or equal to 0 by design, because the truncation functor less than or equal to 0 always lands in there. On the other hand, C lies in whatever is obtained by closing C up under certain operations, and this is C greater or equal to 0. And less than or equal to 0 and greater or equal to 0, these two functors commute up to natural isomorphism, so we conclude that t less than or equal to 0 of C is the same as t less than or equal to 0 of t greater or equal to 0 of C. That's this equation, and then we can commute the two orders, t greater or equal to 0 C of t less than or equal to 0 of C. So it also lies in t greater or equal to 0. And so since this truncation lies in both of them, we can conclude that it actually lies in the heart. So t less than or equal to 0 of C lies in the heart. And we could have started for this argument with anything that already lies in the greater or equal to 0 part, and we would get something in this part. So the next thing that I want to show is that these truncations, as objects of the abelian category of the heart, are small in the sense that if you hom them into a direct sum, you get a direct sum. So again, we let xi, I and I be a family of objects in the heart. And we just showed up here that the direct sum taken in the triangulated category is also a coproduct in the heart in this abelian category. And so we now look at the commutative following commutative square. We look at morphisms from morphisms in the heart from truncation less than or equal 0 to C into the xi's. The xi's don't have to be truncated, they lie in the heart. And I take a direct sum of these, I and I, and I compare this to morphisms in the heart from t less than or equal to 0 of C into the direct sum of the xi's. Here it's unambiguous because the sum in the triangulated category is the sum in the heart, and I would like to show that this map is an isomorphism. That's what it would mean, that these objects, as objects of the abelian category, are small. So we have the adjunction bijection. After all, this truncation is left adjoint to the inclusion, and this lies in the heart already, so this is the same as the direct sum, and now in the triangulated category, and then the original C into xi. Similarly, because the direct sum already lies in the heart, that's what we showed up here, we have the adjunction, truncation is left adjoint to inclusion. So this is the same as morphisms in the triangulated category from C into the direct sum of the xi's. And here we have the canonical morphism. And now one more time, we're using the hypothesis that the objects C are compact, and because they're compact, this is an isomorphism, and hence we can conclude that this is an isomorphism, and this shows that the truncations of the generators are small or compact objects in the abelian category in the heart. Let me now show that the truncations of the original generators are generators in the heart, in the abelian category. Again, there's a little bit to show. While we started with generators in the first place, we're changing the objects by truncating them, so this is not a complete tautology. On the other hand, it's also not too difficult. So let X belong to the heart and assume that it has no maps from any of the truncations of the generators. And suppose that morphisms in the heart from t less than equal to 0 C into X is 0 for all C in the set of generators. So then we know that morphisms from C to the n into X in the triangulated category are 0 for n different from 0. That's the assumption that X belongs to the heart. This is exactly the characterizing property. And also, morphisms in the triangulated category from C with no shift into X is by the adjunction, because X is in the heart, and in particular in t greater or equal to 0, by the jointness property of truncation is the same as morphisms in the heart from t less than equal to 0 C into X, and this we assumed is 0. So for two different reasons, there are no morphisms for any of the shifts of the generators into the X. So most of the time it's because it's in the heart, and then for one case it's by this hypothesis, but in particular X has no morphisms in the triangulated category from any shifts of the generators. So X is 0 in T, and hence also in the heart, hence also in the heart, because the original set C was a set of weak generators. The very last property we have to show is that the truncations of the original generators are projective objects in the abelian category of the heart. And in particular, altogether, this will show that the abelian category has infinite sums and it has a set of small projective generators. And in the next lecture, I will then tell you that such an abelian category is basically a module category or a slightly generalized module category. That's why we're showing all this. Well, let me prove the last claim, that t less than equal to 0 is projective in the abelian category of the heart. So that means we have to be able to lift against epimorphisms. So let f from x to y be an epimorphism in this abelian category in the heart. So what does this mean in terms of the triangulated structure? Well, it means the following. We choose a distinguished triangle. Choose a distinguished triangle, or we choose a fiber, and then x, and then the original morphism f, y, and then f1. So we choose a cone first, and then we rotate backwards one. And being an epimorphism exactly means that this thing that occurs here, which a priori is some object in the triangulated category, actually belongs to the heart again. This is precisely what it means to be an epimorphism. That this object again belongs to the heart, and then this sequence f to x to y is an exact sequence in the abelian category in the heart. So now we pick a generator and we look at the commutative diagram. So for any C in C, the following commutes. So we have here morphisms in the heart from t less than equal to 0 C into x. Here we have whatever is induced by our f, morphisms in the heart from tau less than equal to 0 C into y. This is isomorphic by the adjunction projection that we've already used a bunch of times to morphisms in the triangulated category, C into x. This is f lower star. This is morphisms in the triangulated category into y. this is an isomorphism here. And in the triangulated category, this distinguished triangle leads to a long exact sequence, and the last term here would be morphisms from C shifted by -1 into F. But now F is an object in the heart. That comes from the hypothesis that the original morphism was an epimorphism, that's equivalent to this being epimorphism. But being in the heart means that there are no non-zero morphisms from negative shifts of any of the generators. So this is 0. Because this is part of an exact sequence of abelian groups, this must mean that this is surjective, and that means that here we have a surjection, and that's exactly what it means to be a projective object, that you can lift over epimorphisms. This concludes the proof of part 5 of the theorem, and hence it concludes the proof of the main theorem. And since my time is up, this is all I can explain today. I hope that you like this lecture, despite the fact that there was no equivariant stable homotopy theory in it. After all, this was a pure lecture just in triangulated category theory. But please keep in mind that an application of all this formalism will be eventually that a global functor has an associated orthogonal spectrum that realizes this global functor on pi0 underlined. This is a non-trivial consequence that I am not able to show directly by some Poinsett level construction, so please keep this in mind, because that's the main reason why I'm doing this general category, triangulated category theory arguments. Since my time is up, this is all for today, so all that remains is to thank you for your attention.